Hello, everyone. Welcome to today's webinar. My name is Anthony Lorella, and I'll be hosting the session today, giving you a bit of an introduction, and then we'll be able to take it away with the technical material presented by my colleague. So as we advance here, the topic, as you may know, for today's session is the system level design and validation of high fidelity electric vehicle motor designs. So we'll be going into more detail about what that is and how to effectively do that with our tool set in just a minute. But before we get to that, brief introductions are in order. First, we'll start with an introduction to Maya. At Maya HTT, we help organizations with their digital transformation journey. Actually, Siemens has recognized us as their top North American partner in 2024. We aren't just consulting and systems integration. We at Maya are also in the game of software development with over 30 modules authored for Siemens and used by just about millions across the globe. At Maya, in terms of our team, over 75% of us, I believe now, are scientists and engineers with hands-on experience across multiple industries. So whether you're looking to improve your designs, your simulations, manufacturing, or just optimizing your operations as a whole, our combined experience, be it engineering, software development, or even in AI, uniquely positions us to move you from concept to completion and beyond. So for today's presentation, like I said, I'm not your host. I'll just be introducing today's speaker. And that is my colleague, Anthony Lowther. Anthony has a master's from University of Southampton and previously was part of the development team for some of the Siemens electromagnetic simulation software. These days, he's working with us at Maya and has been supporting our customers in the EMAG space for over 3 years now. So Anthony, without further ado, I'll pass it over to you and let you take us through today's material.
Brilliant. Thanks a lot, Anthony. Yes, it's kind of confusing. There's two Anthonys involved here at Maya. So, as we mentioned, we're going to be talking about designing motors, integrating them into system level simulation, system level designs, making sure that we have all the tools that we need to do that. Now, a big part of that process, we're going to break it down into a couple different little chapters just so you guys know what's going on. We're going to just review for EVs, the current EV landscape, why this integration is so important. Going to look at some computational methods of how we can look at system level simulation, system level integrations before we dive into the component level design validation. From there, we can talk about optimization, extending the use of this tool, and I'm sure there'll be plenty of questions. So, the current EV space, I'm sure plenty of you have an idea what the EV space is like at the moment, but it's absolutely booming. We see a lot of interest from lots of different companies, both established and companies who are total startups and trying to get in on what seems to be looking like a big industry in the near future. Hundreds of companies developing vehicles, and this extends beyond just cars and trucks, but into things like aircraft and heavy industry. As time goes on, we're seeing a larger and larger market share for EVs, both electric vehicles and hybrid electric vehicles. As time goes on, we expect this to expand. By the time we get to 2030, we're going to be approaching a majority of they're slowly approaching a majority of vehicles will be electrified in some fashion. And we all know that there's a lot of legislation coming in the next couple of decades that potentially could force even higher adoption rates than we're seeing naturally at the moment. Now, shifting from the traditional internal combustion engines and platforms into the electric vehicle space, and electrification of transportation has some massive challenges associated with it. When companies are designing a new vehicle, that has to include everything. It's not just a powertrain. It's not just dropping an electric motor in under the hood of an old ICE car. You have to develop a whole platform because you've got batteries, you've got new control systems, you've got new electronics, etc. With internal combustion engines, we had gotten as a world, as an industry, to a place where there was a lot of experience, there was a lot of background knowledge, and it turned into a very fast turnaround pace. We could have new designs tested and developed and pushed out to market really quickly, knowing that we'd be able to meet performance goals without having to build tons of prototypes, without having to go through a very detailed preparation phase in a lot of cases, just little updates, little changes with progressive improvements. Now, when we reach EV development, we have a big challenge where we don't have that level of experience. With that lack of experience, we also have no historical data. We don't know how the platform is going to behave under long time durations, under different loads. We're slowly gathering that information, but the consumer side expects electric cars to be available to progress at the same rate that they're used to internal combustion vehicles progressing. The problem with this is that without the historical data, without being able to use that experience, we don't always know whether the performance will be met when we're developing a new platform without extending the development time, including more simulation, more prototyping to get all the way through it. Now, what we have with the tools that are available to us through Siemens and to you through Maya is ways to accelerate that process, ways to look at integration, look at platform level systems without having to go through costly and time-intensive processes around prototyping and development. So, with that background, we can take a look at some system-level computation methods for EVs. And a good place to start, because not everyone is necessarily familiar with systems-level simulation or computation, whether it be for EVs or any other situation, is we'll take a quick look at what we like to call the V system or the V cycle. This is a nice way of looking at how the design process for any product can go through. And we're going to, obviously have a twist here towards electric motors and electrification. Typically, there's a number of stages, starting from defining operational requirements and sort of system level, overall information, working our way through maybe initial motor design or initial platform design, more detailed design, and then in these days, we often look at multi-physics design. And one of the important bits is that all these different levels combine with physical information, and often when we get to prototyping, we want to correlate our prototypes, our physical test data with our simulation data, and we need to be able to feed back information between different levels of simulation. Your detailed multi-physics design might identify problems that you need to go back to your initial motor design or even your operational requirements to reassess where you're going to go from there. So I'm curious often to find out who you are using, what you are using when you're doing your planning, your development, your simulation. So a quick question to the audience. What level of simulation tools do you guys currently use? There should be a question popping up on your screen any moment now, with a couple multiple choice answers. We're curious just to find out how you guys are using simulation tools at the moment. So we'll give you 30 seconds, a minute to get some answers in, and curious just to see what everyone does at the moment and potentially where we can help you go in the future.
Got some answers coming in already, so thank you. We'll be putting those up in just a minute.
So as we get these answers coming in, it looks like the vast majority of people have answered. So thank you,
Yep,
Anthony, for closing.
no problem. Let's have a look at those now, I guess.
Yeah, and it looks like a lot of people are already doing some level of simulation, whether it be system level simulation, motor design. I'm interested that there's quite a lot of multi-physics design. That's something that we see adopted more and more in industry, but also quite a few people who are not doing any simulation. And I'm curious, and through the feedback here with questions and at the end of the webinar, I'd be curious to hear how you guys think, having seen what we talk about today, how simulation could potentially help you guys in the future. Now, back to the fun presentation at hand. When we looked at the levels of simulation. Now we're going to talk about where we can get those different levels of simulation from the Siemens SimCenter suite of tools. I've replaced the titles of each level with the product names that we get here. And so the system level for overall looking at system platform sort of level simulation, we'll talk about SimCenter AIMASIM. And then as we get into motor design, we have a tool called SimCenter eMachine Design, which is based on some historical tools, two in particular, SimCenter MotorSolve, which came from Infolitica, and the Speed motor design tool, which originally came from the University of Glasgow. As we get into more detailed design, you can see the name SimCenter 3D come up twice in this case, with detailed electromagnetic design, but also reaching into the multi-physics domain. And that's the premier simulation tool offered by Siemens. It's very, very powerful, but with that comes some complexity, which is why we use something like SimCenter eMachine Design to do initial design without having to jump into a fully detailed modeling, detailed simulation, which is computationally more expensive and engineer time more expensive. For today's presentation in particular, we're going to be looking just at those first two levels of design, talking about SimCenter AIMSIM and SimCenter eMachine Design, and being able to work with these two tools in together, being able to develop a system level simulation that ties together directly with a motor level simulation. Often when we're looking at developing e-drives or electric vehicles, there's all sorts of different steps and processes that are going to have to go through, from sizing to component level design to integration to detailed development of things like controls, and all of this tied together with simulation, with physical testing. We don't have time to go through all of that today. So in particular, we're going to be looking at sizing, how we can look at sizing an e-drive, how big does the motor need to be, how hard can we push it, how hard do we need to push it. We're going to look at specifically the motor component design, and then integrating that motor component into a full vehicle level system. When we look at system level simulation, we can talk about lots of different levels of fidelity. And this is often a big question that we get is, how accurate is your simulation? How detailed is your simulation? And the answer is it varies. We can do very basic pre-sizing, general sizing sort of simulation, very basic models of very generic performance characteristics, all the way through to being able to have very detailed models within our system simulation where they'll replicate the behavior of a very specific motor design. And all the way through different levels of detail, we'll have different levels of accuracy, you might say. So more accurate, more detailed simulations might take more time, but they'll give us a much better understanding of how the final system will work. Lower level detail will be able to run through, say, multiple potential options much, much quicker. When we're defining at the system level, we often want to talk about pre-sizing first. If you're developing a new vehicle, a new platform, you might have questions of how big does my motor actually need to be? And as we mentioned, electric vehicles can be so different from traditional internal combustion that you can't just take a one-for-one replacement. The performance characteristics can be very different. The efficiency characteristics can be very different. And so we often need to go back to the drawing board and say, how big does this motor need to be? What sort of characteristics do we need to look at? And we can use AimSim to do this, looking at the requirements. We can use some pre-sizing tools or some size estimation tools that exist within the AimSim environment to build out ourselves a model that we can work with, a model that we can use to size out our powertrain from the motor to the transmission, the battery, all the way through to the final vehicle. We have a quick example here, just a little video that goes through one of these such tools. It's called the Hybrid Optimization Tool. And this is a tool that lets us define the whole system level model. And when we're talking about system level models, that'll be sort of a big sketch, a big chart of all the different little components that are involved in our system, in this case, an electric car, and connections to define how they interact, how in each block and each component acts and how they interact with each other. So here we've been able to say that we're going to build a purely electric vehicle. So we've got a battery and a motor, a vehicle, some control circuitry. We can define some motor behavior. We can define a drive cycle. And so one of the important things when we're defining a vehicle is that there's different ways that vehicle can be treated based on how it's intended to be used, whether it's just going to drive around slowly in a city or in an industrial setting, whether it's a long distance going to do a lot of mileage on the highway. So we often want to test different potential operating conditions. These tools help us choose, say, pre-programmed, predefined standards, industry standards, or even custom standards to see how the system overall will respond to these different tests. And these tools can help us draw out the full system level diagram, as we're seeing just here, where the tool has built out a sketch and we can see all the components starting to come together. We've got a driver and we can define their behavior, how fast do they want to be going, how are they going to treat the different pedals and the different parts of the system, connected into control systems, connected into a vehicle all the way in the top right, and a motor and battery system down in the bottom left. Now, this is where we're going to shift this presentation from, hey, here's some concepts, to here's a practical example that we worked on. So Anthony Lorella and I put together this example. We're working on a project together. And the first thing we had was we had an electric vehicle that needed a powertrain. We put together a system level model. This is a little more complex than we just saw in the video, but the important bits that we want to highlight really are in the sort of bottom central part of the model, in purple mostly, which is things around sizing out the electric motor. So that's just the little circle. It says SM3 with a tilde next to it. And we need to size that out. We're connecting it to a transmission box labeled reducer. We're connecting it to battery and control system, a driver, a vehicle, and the vehicle driving an environment. And this whole system, this vehicle that we're simulating, had to meet a requirement. In this case, the WLTC Class 3B test, which is an industry standard test that tests a vehicle at multiple performance levels, multiple situations. In this case, low, medium, high, and very high speed requirements. So that would simulate, say, in traffic or in a very tight city environment at low speed, medium speed, driving on larger roads, but still intra-city, intercity, where we're getting to high speed, we're maybe going on major roads, touching on highways, and extra high speeds just when maybe you need to overtake that Sunday driver in front of you on the highway. So in this case, we only needed to run, our project only required a single test case, but often there's a lot of different test cases that need to be used. So when you're designing an electric vehicle, I'm curious, how many different drive cycles do you guys look at? Are you looking at a single operating situation? Are you looking at multiple? How do you guys set up your tests? You should see a nice poll questionnaire pop up on your screen. This is a major part that when we talk to people in the industry, customers of ours, and just generally EV manufacturers, different companies, different organizations have different requirements on their tests, whether they're running one cycle, one general purpose cycle, like we just talked about with the WLTC 3B test, or maybe multiple different situational tests, some slow, some fast, some in the middle, some with high loads or low loads. Maybe you're changing the vehicle characteristics, whether that be mass or size, or maybe it's got a trailer behind it.
Yeah, that's a
How are
good
we
point. A
doing?
lot of these driving cycles are going to be application specific.
Yeah, and so we see a big variety in the requirements that people put on the vehicles that they're designing. We'll give a couple more seconds for people. It seems to have studied out. We've got quite a few answers in
Yeah, I'll
already.
put those up.
So it looks
There
like a
you go.
lot of people do a couple simulations. Although I guess I'm a little bit surprised that quite so many people are only doing 1 to 3. I've often seen organizations who like to run 6, 7, 8 different tests. But obviously this very much scales depending on the requirements and what you're doing. So get back to the information that you guys are here to hear about. So the next step, when we've got our system built up and we want to look at how we've sized things, we've potentially looked at some sizing already. We've got an idea what sort of motor size we're going to need. Now we need to get into designing that motor. How are we going to find a motor design that fits our requirements, does what we need it to do, and validate that that does what we need? Now, this is where we're going to shift from AIM-Sim into eMachine design. And the workflow for eMachine design is very template-based. The whole tool tries to be template-based, tries to be very step-by-step, easy to use for designing electric machine. We might start with requirements, in this case, sizing information that came from SimCenter AIM-Sim, and we can define all the general behavior of this machine, what sort of power it's going to use, rough sizing information around the number of slots and poles, geometry, how big it's going to be, what templates we're going to use. And from there, we can talk about winding as well, how it's going to be driven, different drive systems, different particular designs around maybe wire sizing, wire packing, and winding layout. Once we've defined our whole machine, geometrically, winding-wise, so electrically, all this information, push it through the system, And the e-machine design tool will bring out a whole bunch of information. Uh, it does post-processing automatically, can get us nice information around things like speed torque curves and efficiency maps. It can also do things like plotting the internal field so we can see if we're encountering problems with saturation in, say, the back iron of the stator. This allows us to look at preset experiments. So those are the charts that you might regularly see, but also lets us really dive into the detailed simulation analysis of our machine. There's also the ability internally to connect to some very basic thermal analysis. And while this doesn't extend to full CFD detailed thermal cooling capabilities, it does give us a good idea of where might we have hot spots, where might we need to concentrate our cooling capabilities on. From here, we've got a model, we've tested it, we think it should meet all our requirements, and we can pass it on from the e-machine design tool back into other levels of simulation. We can pass it back to AimSim and the system level simulation, as we'll do in just a couple slides time, but we can also take this model out and pass it into tools like SimCenter 3D, where we might go do more detailed analysis in the EMAG space, but also reach out into something like the thermal space or the vibroacoustic space as well. So for our project, we already found a design that was in the Maya HGT library of designs we had worked on previously for an 8-pole, 48-slot IPM design, rated out at 65 kilowatts when it was running at 7,000 RPM, and at this peak efficiency around 94%, which was bang on where we wanted it to be. It was right on the power rating that we needed from our AimSim sizing that we did. It was right up in the efficiency range that we'd be looking for to get the range that we needed. And it was an existing design that we had in-house. So minimal development effort. And we thought, great, off to the races, plug this in, shoot it off to the people who have requested it, job done. But first we had to validate it. And what that meant was that we were going to take the finite element model, the electromagnetic simulation data that came from SimCenter eMachine design, and we're going to have SimCenter eMachine design repackage that into performance tables, loss tables, flux linkages, etc. All this information that could be fed back into SimCenter AimSim, so we could have a detailed system level simulation. How does our vehicle perform with this specific motor in, rather than a generic, roughly sized machine? It's a fairly simple process. On the e-machine design side, we exported a couple files. They were automatically generated. On the SimCenter AimSim side, they were imported. And then it's as simple as hitting run, and it'll run through the predefined test pattern that we requested. Looking at the results that we got, we had really good results coming out at our lower speed. So our low, medium, and high speed tests were bang on the money. We're happy with what we were seeing. I don't know if it shows too well at the moment, but there's a dotted line as well as a solid line in here representing the requested information and the actual performance of the machine. The problem was when we got to the very high speeds. And you can see just as we got up to our highest speeds, where we might have on paper met the requirements for power at the certain speed, the motor couldn't quite deliver enough for that last little bit of acceleration at the high speeds, and it was just tapping out. And that would be, if we implemented this in our vehicle, when you're trying to, say, overtake someone on the motorway, that would be like putting your foot to the floor and the car just cannot get any faster, which can be incredibly frustrating. It doesn't meet the requirements that we needed. So you can see a little better here, right at the top speeds. There's just not enough oomph in our machine to get us to those speeds that we're looking for. So we faced a conundrum. we had a design, we could meet the on paper requirements, and we're pretty darn close here. This is very high speeds. We'd say very rarely used, just overtaking on the highway. Could it be good enough? And what do you guys think? Would this be this not quite good enough result? Would this be acceptable for you guys? If you had to put out this design, would you put it out there, or would you go back to the drawing board?
So the poll for that one is up. Easy, only two choices to pick from here, so let us know.
And often in situations like this, sometimes you might look and say, hey, realistically, that represents such a small fraction of our requirements that we can let it slide. Or you might say, hey, actually, we're going to be racing this thing down the highway all the time. We need to be able to reach those top speeds. So again, like everything else, this is a little bit situation dependent, but the whole point of these simulation tools is to help you make those decisions with as much information as possible. Be sure that you've looked at the data, you know that it's lacking that performance there, and you've made the understanding, the decision that you're going to be lacking that performance. Or, despite the fact that this met the requirements on paper, you're going to have to go back to the drawing board and find a new design. Looks like actually, 2/3, 1/3 split, where actually quite a few people would be okay with this design, but quite a few of you would have to reevaluate, which is interesting. I thought it might go the other way, but there you go. You guys are the ones who are actually doing this in industry. We're just here to
Yeah,
help you along.
I guess it depends how precise the industry requires your
Yep.
performance to be.
Yeah, different industries, different requirements, different expected use cases. So for us, Anthony and I sat down and said this wasn't good enough. We needed to find a new design. We need to adjust our design. But in this case, we're pretty close. So we said, hey, why don't we take this base design? Why don't we just do a little bit of optimization? So that's what we did. We took our base design. We had it already built into the SimCenter tools. We had it connected to SimCenter AimSim. We had it connected to eMachine Design. And we introduced a third tool into this process called HEEDS. HEEDS is a design space exploration, design space optimization tool from Siemens. Connects really well to all the Siemens tools, as well as a fair number of third-party tools. What it allows you to do is to automate a lot of the optimization process. We give a design to it, we define parameters that we want it to adjust, we give it targets, we say off you go. So in this case, we said, hey, we want you to maximize power, we obviously want you to maximize efficiency as well. We also need you to meet a certain minimum requirement. We put a constraint so that it could self-learn. It's got some learning algorithms in it. We said, hey, here's a minimum torque, effectively a minimum power requirement that we wanted it to meet. And that was just to help filter out low power designs. And we gave it all sorts of variables it could play with, things around the magnet geometry, some winding setup, some source power setup, and we let this rip and said, hey, come back, basically told HEEDS, come back to us with a better design. From this, off it went, ran about 60 different variants of this motor, changing little things here or there, whether it's geometry, whether it's winding information. And it came out with a actually fairly well improved design without massively changing the overall machine geometry or the manufacturing requirements. We found a way to push the output power up 20% at maximum power. Now, in this case, it moved the maximum power speed a little higher up the speed torque curve, but that was acceptable to us. That's why we didn't force that constraint, that as a constraint in the exploration. And actually, we saw a slight efficiency boost, about 2% at max efficiency. So the little chart here shows you just the speed torque curves of the two different machines and how the optimized design actually really improved, especially showed big improvements up at um, the higher speed operating points, which is exactly where we were lacking previously. Now we went back to revalidate, same process, extracted the information out of SimCenter eMachine design, put that new design's performance characteristics into SimCenter AimSim, and ran it all over again. And this time we got much better match. We're very, very close to the expected behavior. Only just missing, you can see sort of over towards the right-hand end of the curve, our blue line for our new optimized motor didn't quite match that highest speed peak. But at this point, we've gotten pretty much as far as we need to. And we said, this is enough. We're so close. That is such a small part of our test. This was a model that we wanted to propose going forward, because in our site, in our planning, we basically said the next to find that little bit extra improvement would require a lot more effort. But along with the higher speed performance that we got out of our new optimized design, we also saw much lower losses. So these are two plots of losses between our original motor and our optimized motor. The colors have flipped, I apologize, but we see much, much lower losses in the machine, particularly in the winding losses as we're pushing at the high speeds, and in the iron losses at in the lower speeds as well. So as we're getting up to low speed, high speed, we're seeing much more efficient motor. We're going to be running a lower temperature. And as many people know in this industry is that the hotter your machine gets, the higher those losses are, the more it's going to punish you for longevity, or the more it's going to punish you for power that's available on demand in extreme conditions. So at this point, we sent off our motor design as part of the project saying, we found it. Not only did we find a motor that fit your design, we actually found an even better motor than we had on the shelf already. So having looked at all of this, I'm curious whether this level of integration between different levels of simulation would be of interest to all of you as members of the industry. We've looked at connecting system level simulation and some very initial motor design simulation. But this concept of integration between different levels of simulation, different domains of simulation can be expanded all the way through that V cycle that we looked at, taking this basic motor's performance and passing it up into more detailed performance behavior, into potentially thermal CFD simulations, or vibroacoustics and NVH simulations, to help tie all the different concerns and all the different interests together without having to build physical prototypes and go through the cost and time that it takes to build out prototypes, test prototypes on the bench.
Yep, and you can also consider, what other types of analyses you can enable besides just the one we're showing. So, let your imagination kind of fill in the blanks for what you can do in a connected simulation like that.
Of course. How are we doing? Looks like we've got a few results in, and
Yep.
I'm happy to see that you're all so interested in the integration of simulation across the board. That's what we wanted to show off. That's what we wanted to make you guys aware of. So I'm glad to see that it's of interest. Now, as we get through all of this, I just wanted to talk briefly about some expanded uses, and I'm going to try and concentrate here on the system level tool, AimSim, and where we can expand its uses into other domains around electric vehicle design, and tying it into potentially other physics domains. Things around cooling, being able to design and size a cooling system for your particular, you've now got a motor, now you know what the losses are, now you need to cool it, because otherwise it'll just run itself to death and melt itself. Um, and we have the ability there to build out system level cooling operations. We can tie that back to other simulation level, other more detailed thermal simulations to make sure it's behaving properly. And in fact, the latest version of AimSim, which was released just a couple weeks ago, takes this one level further and really breaks down the thermal behavior of the motor. So being able to tie in detail the motor performance at different temperatures as different components change temperature in the motor, along with your cooling system, and tie that all really well together so that you get an even more accurate representation of how your machine is going to behave over different duty cycles, different cooling conditions, different ambient conditions. The other things we can do with this system level tool, AimSim, is really being able to connect into all sorts of different drive control simulations and testing, being able to run functional tests with a model in the loop, or even going into the real world and testing it with real-time validation hardware in the loop systems. These are all capabilities that AimSim has within it to be able to run these different connections, connecting motor models to controller models to battery models, etc. And the last little bit that we want to mention is we talked about vibroacoustics, and we can do some interesting vibroacoustics at the system level. Just knowing from our motor design, we can look at how things such as different inverters or different control methodologies can change the input parameters into your motor, and we can look at how that might affect how the motor behaves. We can look at how that might affect the harmonics, and obviously that impacts vibration and acoustics at a system level. And we can help that to drive our detailed NVH and vibroacoustic simulations down the line when we start including things around housings, around mountings, and all the whole physical system that we might have built out in a 3D CAD platform doing vibrational analysis. So a quick summary. We've been fairly quick about this. I know I might have rushed through some of the information, so I'll have a moment for questions in a couple slides. But we've looked at system level simulation, how we can look at motor pre-sizing, how we can choose a motor that fits our particular use case, how we can use dedicated motor design tools to fit that use case, how we can test different architectures, and how we can then take that motor design, validate it, and validate the whole system performance. Are you going to get to that top speed? Are you going to be able to accelerate that hard using a high fidelity representation of the motor that we designed? And overall, often we find situations where we can find something very close, but we do need to do a bit of design space optimization, exploration to pick out little performance improvements that we can find for better system level performance, for better component level performance. And using design space optimization tools such as HEEDS can really help us do that stage in a much reduced time, particularly reducing the amount of engineer time. Someone doesn't have to sit there and make those changes for each individual iteration. HEEDS can go off and run dozens, hundreds, thousands of designs on its own, totally automated. You come back the next morning and you've got all the options and results in front of you, and you can just take the time to choose rather than to have to come up with little variations. So one last question for you all. How would you like to explore the topics we talked today? We can set up things like one-on-one meetings. If anyone is curious, you can drop me a line, you can drop my colleague Anthony a line. and we can set up meetings. We can offer evaluations or trainings on all these tools so that you can try them. You can learn how to better use them if you already have them. And I'm honestly really excited to present these webinars and to show everyone what we can do. So if you're interested in further webinars, I really encourage you whether to reach out to myself or to Maya with topics that you might be interested in seeing a webinar about, or just drop it in the chat in this webinar. You know, when we present webinars, we want to make sure that the webinars are things that you're interested in, the wider audience is interested in seeing, because I can set up webinars about all sorts of topics that'll put you to sleep. But
Yeah, we don't need a poll to tell us that we're interested in talking about these things.
yeah, so what are you guys interested in?
So let me put those up for you now. I think we've got quite a few in.
Sure. Oh, I'm happy to see you guys want more webinars. Please give us suggestions of what you want to see, what you want to talk about in future webinars, because that's sort of key for us to make sure that we're giving you the information that you want, showing you what's useful for you. Certainly, if you're interested in meetings, evaluations, benchmarking, or acquiring the software, reach out to us. Reach out to whether it's myself or Anthony Lorella or any of the team here at MyHGT, and we'd be so happy to get you involved. My email address is up on the screen. We have a couple of QR codes that'll get you the right place to go find more information about this topic and others, and also ways to contact us, reach out to us, to book those meetings, to book those evaluations, or to give us suggestions for webinars, which would be very, very nice. I'll leave this up on the screen so you guys have a moment to write things down, scan those QR codes as you need. Before I open the floor to questions, I just wanted to say after the webinar, you will likely get an email in the next little while asking you whether you enjoyed the webinar. Just a couple little questions, should only take a couple minutes to fill out, just to give us some feedback on whether the webinar was useful, whether the information was useful, how we can improve going forward. And I'd really appreciate it if you guys could fill out this questionnaire when it comes out. And without further ado, feel free to ask questions. There's the ability in the webinar interface. You should be able to ask questions through the question interface. There's also a chat interface if you want to drop messages in chat where it's more visible.
So we've got a few already.
Yep.
I can kind of shout them out here. If there are any more, go ahead. Otherwise, always available for questions later. But the ones that are in here, I'll start at the top. Yeah, generally, is the session recorded and be shared afterwards? Yeah, I believe there will be a recording that should be available of this one.
Yep. Yeah, this was recorded. There should be an email that goes out once the recording is sort of been set up. You should get a link in your email as to how to get to it.
Now, the next one, more technically related, Anthony, what will be the acceleration of the vehicle? That is a good question. I'm not sure if we have the figures for that in the presentation. The model is certainly capable of figuring that out.
Yeah, we don't have that in the presentation, so I can't just hop to a slide and show you the acceleration or the peak acceleration, I presume is what you're asking about. But certainly when you're looking at a system level model, a vehicle level model, you can definitely extract, here we tested it against a particular benchmark test, a particular test profile, but you can also just ask it, how fast could you accelerate? How fast could you go 0 to 100? That sort of information is all in there. You want to know how to do on a quarter-mile run? You can ask it, it'll tell you.
And let's see, there was another one. Oh yeah, in terms of the connection, so there was a question asking if we can connect this to other types of analysis, like like a structural mechanical model, for example, um, for the transmission system.
Yep. So when we look at something like a transmission, or say the larger system, maybe you want to look at how you're mounting the motor in the vehicle. We can go back partially the transmission stuff, the active stuff. We can look in SimCenter AimSim that has capabilities and tools in there to do transmission, some basic transmission analysis. But we can also go back to our detail level design, and we can tie our system level requirements back into a detailed design, build out a 3D model in CAD, run structural and vibrational analysis on the transmission, on the vehicle as a whole, and see how that behaves, tie those results back to our system level simulation.
Hmm. And last one, what exactly is meant by new capabilities in thermal simulation?
So what we had previously was the ability to go from loss information. We can, taking losses, fairly easy to figure out how much energy is being put into a component, fairly easy from there to figure out how much that component's going to heat up. And we can do at the aim sim level, we can do some information around how much you're cooling it when you've defined a cooling system. This next level of integration is really around also understanding at the system level how those thermal behaviors are going to affect the motor performance. So we could do simulations at the motor level at different temperatures, at different component temperatures, and manually feed all that information back into the system level. These new developments in the latest version automate a lot of that process. It just makes things a little nicer, quality of life improvement, as it were.
Hmm. Understood. Yeah, and that's an interesting new one, and that kind of highlights the ongoing development of these capabilities. So, this is an interesting, relatively new, say, avenue of exploration that unlocks a lot of, let's say, ease of use to getting answers for our different analyses. So, I guess in short, watch this space for even more enhanced capability. Um,
Yeah.
so. I think that takes us to the end here. That was the last question that I was able to see from the list. Um, a big thank you to everybody for your time and attention today. Thank you to Anthony for taking us through the material. And like he said, if there are any questions or comments, please do let us know. Otherwise, have a great rest of your day.
Thanks a lot, everyone. We like seeing you all here.